So the first thing we're going to talk about today is the composition of blood. So if we have a blood tube here, the little red lid, because why not? So inside this tube, if we were to take the tube, spin it down so we can see all the components of blood, right in here, we'd have a line. And all this down here is our red blood cells, so RBCs. And then everything above it is plasma. But we do have a little bit right here, I'll draw it in blue. These are our white blood cells. And sometimes it's called the buffy coat. Then everything up here until the top, this is our plasma. And in our plasma, we have things like our proteins, our albumin, electrolytes, metabolites, urea, all that kind of stuff. That's what's found in the plasma itself. So also oxygen, like gases, O2, that stuff, that's found in the plasma. And the plasma is mostly made up of water. It's a very watery substance with a bunch of other proteins and that kind of stuff in it. So let's look at red blood cells for a second. So we have a red blood cell. We're going to look at it kind of from the side here. So we have a little dip and it comes up, comes around, dips back in. That's the rough shape of a red blood cell per se. In a red blood cell, we have all sorts of protein. We have some proteins and stuff, and the one we're going to look at is hemoglobin. So hemoglobin, it has a bunch of different it has 4 different subunits and an iron center. And so we can draw this kind of right here with some different subunits and an iron center here. That's a hemoglobin. It's made up of heme groups, globulin proteins, and this iron center. So the body uses red bone marrow to make red blood cells, and it makes about 2 million every second. And that red bone marrow is mainly found in the tips of the femur, humerus, and the iliac spine. And because we're making so many red blood cells, we need to break down red blood cells. And to do that, the red blood cells go through the body, they go into the spleen, and the old red blood cells, the ones that have been there for about 120 days, they're not as flexible anymore. They don't bend and move around as much. So what happens there is they become stiff and get caught within the network of the spleen, the spongy network. And when that happens, macrophages will come and they'll chew this up. They'll eat up that red blood cell, and most of it will be recycled. The globulin proteins, we'll focus on the hemoglobin here in a second, but a lot of the stuff, the components of the red blood cell, will be put back into circulation for recycling. However, the hemoglobin, it's a little different. It's special. So if we were to look at the hemoglobin, the heme, it has to be broken down special. The globulin proteins, those amino acids are going to be broken down, put into the bloodstream so that we can reuse them. The iron center, it's going to be put into the bloodstream. It's ferritin, and then it can be used as transferrin and all these different things. But the heme, so if we look at the heme, it needs to be broken down in a different way. So what happens is the heme will be converted into what's called biliverdin. So we have heme becomes biliverdin. And how this happens is an O2 molecule comes in and that iron center comes off. So we have Fe coming off. And after that biliverdin is made, we have another transition where it becomes bilirubin. Bilirubin. I think that's spelled wrong, but that's okay. You get the point. Bilirubin is special. It is what makes people have jaundice in the skin and when they're having liver failure and stuff. And we'll get into that right now, because bilirubin, it attaches to albumin in the blood and it is taken to the liver. And there's my liver. I'll just label it because it doesn't look like a liver. But the bilirubin will come in, and as it comes in, the bilirubin gets what's called glucuronic acid put on it, and it becomes conjugated bilirubin, or bilirubin with a bunch of sugars and glucuronic acid attached to it. That makes bilirubin water soluble again. So what will happen is over here we have the common bile duct that's coming down, and we have our intestines coming off of that right there, and we'll extend this out a little bit over here. So this conjugated bilirubin, it'll come down, come through the bile duct and into the small intestine. Once it's in the small intestine will actually take those glucuronic acids off, and it will become what's called urobilinogen. So we're just going to put UB for short. So urobilinogen now has all those different glucuronic acids taken off, and it can do one of two things. So urobilinogen can actually continue down the small intestine to the large intestine, and there it will become, it will be made into stercobilin, which is brown, and it gets excreted in the stool. Also, urobilinogen can also come out of the small intestine into the bloodstream. We'll draw a little blood vessel here, a little tiny one. And once urobilinogen is in the bloodstream, it can either come back to the liver to be conjugated again and go through this cycle, because urobilinogen is really just bilirubin with a few different changes, because once it's conjugated, those glucuronic acids are taken off, and it undergoes a slight change, but it can become conjugated again and go through the cycle. Or it can be taken over here to the kidney, where it will become urobilin, a different urobilin, and it will be excreted in the urine. It's a yellow color, it will be excreted in the urine. So because there's a process to break down heme, there are different pathways to get rid of it, and these are those pathways. Heme to biliverdin to bilirubin. We conjugate it in the liver, it comes down, and it becomes urobilinogen. That can either become urobilin in the kidney to go to the urine, or it can go back and become conjugated, go through this again, or stercobilin, which will be excreted in the stool. It's a brownish color. All right, so the next thing we need to talk about is hemostasis. So hemostasis is how we clot. So I'm going to draw a big old blood vessel here. Got one wall and the other wall. And we have all these endothelial cells here. Like that. Not great. And they're also down here, endothelial cells. Okay? And then outside, we have the basement membrane that comes along the outer edge of these blood vessels. That's coming down here and up there. That's the basement membrane. Okay, so what happens when we damage a blood vessel? To start off, we need to look at platelets. So platelets, they're little tiny like grains of floating in the blood. And they have different receptors on them. One of the receptors is a von Willebrand factor, or VWF receptor, because we have these endothelials that are releasing the VWF factor. So VWF comes down, we're going to draw it as a little triangle here. It comes down and it'll actually attach to that site. But this doesn't activate the platelets because this receptor here is a mechanoreceptor. So it'll activate the platelets when there's some sort of mechanical action. They also have another receptor on here that is a VFX receptor, or a thromboxane receptor, THX, thromboxane. So that'll come in, and that actually activates these platelets. So if we have some THX, some thromboxane come in and it bind, that will activate this platelet. And also ADP. If we have some ADP that comes in, we'll have a receptor here. ADP will come in and activate that platelet. So what happens when these platelets get activated? So let's say we have some damage here to the blood vessel wall, and one of these platelets is coming by. That von Willebrand factor, the VWF, it's already connected. So what happens is it'll come through right here, and that factor is attracted to the collagen here. So it'll attach to that collagen, and that is attached to that sensor. I'm going to blow it up here for a second, and attached to the platelet. And when this happens, that pulls on that platelet and activates it. So it turns it into like this kind of octopus looking thing, which has different granules in that. So it has some dense granules and some alpha granules. We'll just color them like this. So the red are alpha granules. The black, these are dense granules. And those granules, they will excrete these different factors. So the THX, the ADP, calcium, they'll come out of these different granules. And they'll go back and they will actually kind of bring in more platelets and attract more platelets. And they'll attach and begin to form what's called a platelet plug. And as that platelet plug is forming, we have some stuff that needs to happen in order for those to stay together. So as more come in, we'll kind of draw them here. We got some more platelets coming in. They need to be connected somehow. And in order to do that, we have fibrinogen. We have little fibrinogen bridges that form between them, kind of holding all of these together. The little fibrinogen bridges, they hold those platelet clumps together to begin this process. And another way that we can actually stop this bleeding a little earlier, like it begins to stop the bleeding, is by like vasospasm or vasoconstriction. When there's damage, it'll kind of constrict, and that helps bring platelets and stuff into clot, but it also limits the blood flow coming through. So this is how platelets are activated and come and attach and begin to form that platelet plug. And then the last way, the third way that we kind of solve this problem is through the clotting cascade. I'm going to erase these platelets, but know that they are still here. They're still chilling there, forming that platelet plug. Because I need that space to write. There's two different pathways. There's the intrinsic pathway and the extrinsic pathway. The intrinsic pathway is that because all the factors that we use in the intrinsic pathway begin in the blood. They're already in the bloodstream and they come. So what happens is factor 12, it'll come in and it's attracted to this collagen as well. It'll come in, it'll bump into that collagen, it'll become activated. So we call that 12 activated. And then 12 activated will activate 11, factor 11. So we have factor 11 comes in and it becomes factor 11 activated. And factor 11 will actually activate factor 9. So here we have factor 9 and it becomes factor 9 activated. And when we add factor 8 to factor 9, we activate factor 10. So 10 comes in and it becomes 10 active. And this is the intrinsic, because once we have factor 10 active, we begin the common pathway. And the common pathway is we take factor 3 and it becomes factor 3 active. And then we have factor 2 that comes in and so factor 3 to factor 2, right? Oh wait, no, wrong. So that's wrong. Factor 3 is the extrinsic pathway. So factor 2 will come in and become factor 2 active, and that'll activate factor 1. So factor 2 and factor 1, they have special names. So factor 2 is prothrombin, and factor 2A is thrombin. And then factor 1 is called fibrinogen. And factor 1A is called fibrin. And fibrin and fibrinogen, they are important because, like I said, fibrinogen, it is forming those bridges across the platelet plug, holding it in place, kind of giving it that structural integrity. And fibrin, once it's activated, it begins forming what's called the fibrous network or the fibrin skeleton, something like, they call it lots of different things, but it begins putting like these kind of wispy threads of fibrin around the platelet plug, and that'll catch red blood cells and other platelets and bring them in to help clot that up, and it'll hold it all together and kind of catch it in a web. So that's the, up until factor 10 right here, this is the intrinsic pathway. Now we'll look at the extrinsic pathway. So I'm gonna put another hole here, just for the sake of convenience. So we have factor 3, it's called the tissue factor. So factor 3 is out here in the tissues, and it'll come and it'll activate factor 7. So factor 7 will come in and become 7. That's terrible. 7 active. And so once 7 active is here, it will also, it'll activate factor 10. So that'll come down, activate factor 10. And so this little step here is the extrinsic pathway. We'll write that in red. Extrinsic pathway. And that is because factor 3 isn't in the bloodstream, it is in the tissues, and we use that to begin clotting cascade. Let's see. Okay, so those are the clotting cascades, and remember there's also that platelet plug here to help plug everything up. And then these are also helping with the clotting and getting to this fibrin and fibrinogen to really get that fibrin skeleton to there to catch stuff and make a clot. And the last thing that I need to talk about is how do we regulate this? So let's just say we're going to look here at the top and just this one little clot that we have here. So say this becomes a clot here. That's our blood clot. Okay, after a while that blood clot, everything in it's going to heal, and the actinomycin in the platelets and everything is going to pull that gash, that cut closed, and we're not going to need this blood clot anymore. So what happens is we have something, a zymogen in our blood that's called plasminogen. Plasminogen will interact with what's called TPA. So TPA will interact with that, and this interaction takes plasminogen to plasmin, and plasmin will come through and it'll degrade that blood clot. And how it does this is it will degrade all the components of fibrin. So it'll take and it'll decompose fibrin, so that fibrin skeleton is no longer as strong, and you can peel that scab off, or it'll fall off, or something will happen, but that will no longer be there. And this is how we manage hemolysis. Hemolysis is once it's done, or once if there's a clot that we don't want in the bloodstream that's forming, this will come in, TPA will turn plasminogen into plasmin, and we will break down that clot that we don't want, or the clot that we do want that's no longer needed.